Alright, so we move on to sort of the next general idea. We just finished up enthalpy of formation, and then we move into just the idea of getting the enthalpy of reaction for any given reaction, whether it's formation, combustion, solution, anything. We call this the Big Mama equation, and the reason it's the Big Mama equation is Mama is in charge of everything. And this is one of the most commonly seen concepts on the AP exam because it applies to all things thermodynamic, whether it's enthalpy, entropy, Gibbs free energy, all of it. So the enthalpy of a reaction overall, we actually did this in the last example, can be determined from the enthalpy of formation of the reactants and products. So again, you might need an enthalpy table in the textbook. For exercise 17, we want to calculate the standard enthalpy change for the dehydration, so loss of water, of magnesium hydroxide to give magnesium oxide and water liquid. Since we are talking about enthalpies here and changes, we do need to consider the state. So we'll begin by writing our equation. Okay, and to calculate the standard enthalpy change, then we're going to be dealing with subtract the products minus the reactants. So it's not required to write this out each time, but I'm going to do it for a couple of times just to kind of get the point here. We would take the products, so we do need a balanced equation, so we need to multiply it by the number of moles. So 1 mole of the enthalpy of formation for MgO plus 1 mole times the enthalpy of formation for water minus 1 mole times the enthalpy of formation for magnesium hydroxide. So that got kind of small there. So overall, the only thing we have to do here is just plug in the values from the table. So if you go and find your standard enthalpy table, magnesium oxide in its solid form would be 1 mole, so it's just the same thing, times negative 601.70 kilojoules, plus 1 mole of enthalpy of formation for water, specifically as a liquid, is negative 285.83, and again I'm reading these values off of the table, and then subtract from that the enthalpy of formation for magnesium hydroxide, which is negative 924.7 kilojoules. Okay, so we add these two values together. They're both negative, so that becomes larger negative, and then minus a negative, so we end up with a positive value there at the end. So when you add all these values up, you end up with 37.14 kilojoules of energy, which means that this reaction is endothermic. So that's a very just generalized case. That would be a decomposition reaction or a dehydration, however you want to look at it. You can look at also specific types of enthalpies of reaction. For instance, anything where you're combusting would be some substance, we'll just call it X, plus oxygen makes some kind of oxide. And we don't even know what the ratios would be. This is, your standard of fuel, CXHY plus O2 yields either CO2 in water or CO in water, or it can also be a metal oxide or a nonmetal in an oxide. For example 18, we're talking about propane, so that's a pretty straightforward one. Propane, prop is 3 carbons. Ane means we only have single bonds again, so that's C3H8 plus O2 yields CO2 and water. It says please assume water is a liquid. So we need to balance this equation. It gives me 3 C's. 4 times 2 gives me 8 H's. and that gives me 6 plus 4 is 10 oxygen, so divide by 2 to get 5. And so we want to figure out the amount of heat evolved under standard conditions when 1 mole of propane gas burns in oxygen to give the usual products of combustion. So we're going to assume that this is an enthalpy of combustion and that we can use those formations just like we did before. So it's going to be 3 moles of CO2, and the enthalpy value for CO2 is negative 393.5 kilojoules per mole. And then 4 moles of water, and liquid water is negative 285.83 kilojoules per mole. And then we're going to subtract, I'm going to do that down here so we have a little more space, the enthalpy of formation for the propane. We have 1 mole of that, and that is negative 103.85 kilojoules per mole. And then 5 moles of oxygen, however, oxygen is in its standard state, so it's just 0 kilojoules per mole. When we multiply and solve for our reaction, we end up with negative 2220 kilojoules, and that counts for 1 mole of propane gas because that's the amount that we started with. Okay, if we continue on from exercise 18 on to 19, what we're going to do here is we're just going to kind of look at the differences between enthalpy of combustion and enthalpy of formation, both of which are just specific forms of enthalpy of reaction. Again, to have combustion, you have to have something mixed with oxygen that makes some kind of an oxide, XO, or your standard fuel, CXHY plus O2 yields CO2 and water, or maybe CO and water. And then for formation, you have to form 1 mole of one product from the elements in the standard state. Alright, so those have to be the qualifications. For A, we have carbon, we can assume it's solid carbon, I suppose, plus 1/2 oxygen makes CO. So in this particular case, we are making 1 mole of carbon monoxide. We're making it from the elements in their standard state. And we are also having something mixed with oxygen. So I would venture to say that that was actually a both. And there can be some argument for multiple answers on some of these. Some people would not want to call this a combustion because it's, not your commonly type seen combustion. That's kind of why I wanted to show you some of that up there. For B, we have carbon monoxide plus 1/2 of an oxygen yields CO2. We are forming 1 mole of product, but we're using something that's not an element here. So this could not be considered an enthalpy of formation. You might consider it a combustion. So I would say it would either be an enthalpy of combustion or neither. And the reason I might even say neither is that you're really not supposed to have a fractional coefficient unless you're talking about an enthalpy of formation. For C, we have methanol plus 3/2 oxygen makes CO2 and water. Well, this one, of course, screams combustion to me. It obviously can't be formation because we're making 2 different substances here, and we don't have the elemental forms on the reactant side. So you can, again, either call this one enthalpy of combustion or possibly neither, because we are talking about a fractional coefficient here again. For D, 8 carbon plus 9 hydrogen makes C8H18. It's not a combustion, makes something that would probably likely combust, but it does make 1 mole of product from the elements in the standard state. So that would be an enthalpy of formation. Oh, and I just realized I'm leaving off all of my knots here. So we're assuming these are all happening at standard state, or standard conditions, excuse me. CH4 plus 2O2 yields CO2 plus 2H2O. Classic enthalpy of combustion. definitely not formation. For F, we're making 1 mole of iron chloride, iron 3 chloride, but we're making it from iron 2 chloride, which is definitely not an element, so that cannot be formation. There's no oxygen for anything to combine with here, so that one is definitely a neither. And then finally G, S plus O2 makes SO2. Again, we have a nonmetal oxide being formed that could be considered combustion. And we're also making 1 mole of sulfur dioxide from sulfur and oxygen gas. So that should be both. All right, exercise 20 is very similar to what we did in exercise 18, only this time we're actually solving for a different part of the equation. We have calcium chloride reacts with